Welcome to Everyday Mathematics. Today we are going to look at what is called the Cauchy-Schlomlich transformation. And what this transformation says that if we have continuous functions such that you integrate them, and this continuous function is f open bracket the square over x minus bx integrated from 0 to infinity. That's the same as that same function integrated from 0 to infinity times 1 over a, right? So we're going to show that, and this is part of the problem that is in the almost impossible integral sums and series book, and this is problem 51, and we will dub it 51a. So this happens when a and b are greater than 0. Okay, so let's go ahead and see how we may be able to solve this or prove that this relationship actually holds, right? I'm going to prove that the integral from 0 to infinity, or x tending to infinity, of f ax minus b over x squared is the same as right? So we need to prove this, and what we do is we're just going to put that in a rectangle rather. So what is our proof going to look like? The first thing we're going to do is we're going to say let x be equal to b over ay. And what that means is that dx dy is equal to negative b over ay squared. And thus, when you multiply both sides by dy, we have dx being equal to negative b over ay squared dy. So this is an important thing for us. Then let's look at the limits, right? When x equals to 0, what does that mean? It means that 0 is equals to b over ay, and since b and a are greater than 0, what that means is that y tends to infinity. When x tends to infinity, what that means is that y tends to 0. Therefore, 0 that is equal to infinity 0, and in the y domain f, ax from here means we have b y, and then b over x is the same as ay squared, and in place of x, dx we have negative b over ay squared dy. Okay, and then because we do have this negative sign here, we can flip the limits so that now we have a problem that is b over a 0 to infinity f, because we have a square in there, we're going to have ay minus b over y squared 1 over y squared dy. So what this tells us is that the integral from 0 to infinity of f ax minus b over x squared dx is the same as b over a 0. So we're using this integral here now. F ax minus b over x squared squared. And if these two integrals is dubbed a, then it means that if we add them together, then we get is now equal to, we can pull this function f of ax b over x, and then we have we could pull 1 over a out so that we have a plus b over x squared, like that. So what else do we do if we say let t be equal to ax minus bx? What does that mean? It means that dt dx is equals to a plus bx squared, which means that dt is the same as bracket a plus b over x squared dx. So this part here can be substituted for with dt. So let's box that up. When when x equals to 0, what that means is that t tends to negative infinity. When x tends to infinity, t tends to positive infinity. So what does that tell us? That tells us that our problem is equal to 1 over a negative infinity positive infinity f t squared, and this is dt. Okay, so using this guy here, what do we have? We say 2a, which we had, is the same as 1 over a negative infinity fx squared dx. But we see that x is squared in there, so we can say that this is the same as twice a from 0 to infinity of fx, right? And therefore a is equals to 1 over a small a or lowercase a, the integral from x equals to 0 to x tending to infinity of fx squared, right? So we have really proven our integral there. So we can now say reliably that a being equal to the definite integral from x equals to 0 to x tending to infinity of f x minus b over x squared is equals to 1 over a 0 infinity f x squared. So this here is Cauchy Schlomlich Transformation. Okay. So without much ado, it's been an absolute pleasure just sharing this small window into this transformation. My plea to you is if you haven't subscribed to our channel, please consider subscribing to our channel. In the next one video, we'll actually show how to apply this technique into a real integral problem. So without much ado, until next time, bye-bye.